as Monica mentioned, I'm going to try to give you a sense of what our ideas are about the dark matter, what it might be like, and also the ways in which scientists around the world are trying to find it experimentally, individual bits of it. Dr. Linker talked to you about how we know that the dark matter is there from the effects of dark matter gravitationally, so not from any individual bits of it. Right now, what we're trying to do around the world is find individual bits of it. So that's what I'll be concentrating on. Well, actually, I'll skip this. This is something that Dr. Linker already talked about. So the first question is, what is the nature of this dark matter? Well, how do we generate ideas? We have to have ideas about what the dark matter might be like and then test them. Where do we take our ideas from? Some of the so-called natural ideas are ones that arise, are ideas that arise from other areas of physics where we are already working on problems, and they happen to provide dark matter candidates. And we call them natural only because we already know these other problems already exist, and they seem like they could be tied into the dark matter problem. There's another class of ideas called ad hoc ideas, where we invent ideas really focused on trying to answer the question, why is there dark matter? So one example of an ad hoc idea is the idea, well, maybe through some unknown physics in the very early universe, a very small fraction of a second after the Big Bang, a bunch of black holes were created. That's an ad hoc idea. An example of natural ideas are two of the big problems that we're trying to answer today in physics is, why is gravity so much weaker than the other forces in nature? The attempts to answer that lead to a field or a proposal called supersymmetry. I won't go into the details of that because I'm just trying to illustrate the method for generating guesses, and there's just too many to go through. But this general attempt to answer this big question provides as a side benefit candidates for the dark matter, weakly interacting massive particles that arise naturally from something that has nothing to do with all the astronomical evidence that Dr. Linker talked to you about. Likewise, there's a big question that we don't know the answer to. Why do we live in a matter universe? In the very early universe, in the Big Bang, there should have been equal amounts of matter and antimatter created, and at some point, a small fraction of a second after the Big Bang, the amount of, or the matter and antimatter went through annihilation processes, and by some unknown process, we're left with only matter in our universe and almost no antimatter. And so attempts to understand the answer to that question, which go by, among other things, this name, also provide candidates, particles, sort of for free, which could be the dark matter. And so these are two examples of sort maybe more natural, let's be honest, guesses about what the dark matter is. Okay. I've given you just a couple of examples. I want to emphasize the point. Here's one of the first omissions that I referred to in the front of my slides. There are many ideas about what the dark matter might be like. This is a partial list of the names of different ideas about what the nature of dark matter might be. Some of them are ad hoc, some of them are natural. Okay? And this figure that you see here, the details aren't important, but these colored regions all refer to ideas that are over here. This is a plot which shows one property, effective size of the dark matter particle, and another property, the mass of the dark matter particle. And if we examine at some level these two axes, we're going to see something astonishing. The effective size, which is a measurement of how likely it is that dark matter would bounce into ordinary matter, spans a huge range of possible sizes. The biggest size is 1,000 trillion trillion times bigger than the smallest effective size candidate. Likewise, there's a whole range of possibilities that each of these theories give to the mass of those particles. And the effective size ranges from the biggest one is 1,000 trillion times more massive than the least massive one. So the main point to make here is that, as you would expect from this, no one detector could test all these ideas. And so there's a large number of experiments, in the tens of experiments around the world, each of which is different, each of which, or many of which, are addressed at different regions in this theory plot. And today I'm just going to point out a couple. I'll point out one that's related to the type of dark matter search that we're doing at IU South Bend. And just for variety, I'll point out another example so you can see some of this variation in characteristics that I'm talking about. So these axions, which come from the question, why do we live in a matter universe and not an antimatter universe? One of the characteristics of a type of particle, the theory attempting to answer that question, produces is a particle called an axion, and this axion has very interesting properties. It can be created by the collision of photons, particles of light. And the sun generates enormous amounts of light from the fusion reactions going on there. When I'm talking about light, I'm speaking somewhat poetically because this is light that our eyes are not sensitive to. These would be gamma rays. And the light here is actually magnetic fields that are inside the sun. And so these particles of light can interact, annihilate, and create an axion particle, if this theory is true. And so the sun could be a source of these particles which were created in the early universe, but now would be intensely created inside the sun and streaming towards us. So we could set up detectors on the Earth to sort of reverse this process. You set up a big magnet, a very strong magnetic field, and these axions come through, and every once in a while the magnetic field from this very strong magnet will interact with the axion, turning into an X-ray. So we could see evidence for this, if it exists, by having a sudden amount of X-rays when we tune this detector just right. Now, each of these particles would be very, 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 very light in comparison with the types of dark matter that we're looking for. By the way, I do see a number of students in my class, so this will be familiar to you. If you have questions along the way, please, don't hesitate to stop me. I know we'll have questions at the end also, but if I've said something you don't understand, don't hesitate to raise your hand and call on me. Okay. A different type of dark matter comes from those attempts to understand why is gravity so much weaker than the other forces. And as I mentioned, as a side benefit of that theory, one of the types of particles that would exist could exist if that theory is correct, is a so-called weakly interacting massive particle. So where would these things come from? These things would exist from a very early time in the universe, about a billionth of a second after the Big Bang. the universe was an extremely hot, dense state. And you had particles like photons colliding with each other, and electrons and positrons colliding with each other. And this is the one equation we're going to see the whole night, Einstein's relationship between energy and mass. And all this tells you here is that if you've got enough energy in collisions, you can make as big a mass as you want. That's what this relationship tells you. So in the very early universe, where everything was moving around very energetically, and when they collided, you could make really massive things. So the idea is that in the early universe, things were moving around so fast that these very large mass particles were created. And in the simplest version of the story, there are many versions of this story, the dark matter was being created and annihilated and reached sort of an equilibrium with ordinary matter. But then the universe started to cool when it expanded, kind of like a gas that if you blow air out of your mouth like this, it's very hot. If you let it expand when it comes out of your mouth like this, it's cooler. The universe was doing the same thing. So when the universe cooled off, the amount of energy went down, and suddenly you couldn't make dark matter particles anymore. But you were still annihilating dark matter particles to create ordinary particles. And so we started losing dark matter particles. But at some point, the universe expanded so much that dark matter particles couldn't find each other anymore because there was so much space for them to be in. And so the idea is that these dark matter particles have been frozen into the universe since that early time, about a billionth of a second after the Big Bang. And they're going through everywhere right now. Where are they? They're right here. They're going through your body right now. We know that they're in the Milky Way galaxy because, as Dr. Linker described, we've observed the rotation of different parts of the Milky Way galaxy. And we know that there's about 85% of the mass that's unaccounted for. Only about 15% is accounted for by what I'm going to call atoms, which includes everything, including big clouds of gas and stars, black holes, etc. That's only about 15% of the stuff that's out there. And in fact, at our location, there's about one dark matter particle in every fist at any time. Okay, so one of the questions, since we want to find individual bits of the stuff, is how do we do it? And as you might have guessed already from what we talked about, there's a wide range of possibilities about what the nature of the dark matter could be, which makes designing something that can catch it very challenging. So this is an analogy that actually a podcaster suggested to me, which is, we don't know if the dark matter is more like a mole or a mouse or a bat. If it's like a bat, and we've designed things that can catch things that are underground, we'll never see them, etc. We can go through permutations of that. And that's why you'll see that we have many different techniques to try to see the dark matter. Let's take the macroscopic view. Even within this small subsection of dark matter candidates that we've narrowed our view down to, there's three general ways that we're looking for this type of WIMP dark matter. One, scientists are looking for dark matter that's annihilating, say, in the center of our galaxy. Annihilating and forming high energy particles that we can see, like photons, which would have characteristic energies that we could see. Another way that we're trying to see them is by making them in accelerators. And in fact, our colleagues at Notre Dame are participating in an experiment which is looking for dark matter in this way at the Large Hadron Collider in Europe. So they're smashing together protons at high enough energies. Remember our one equation, E equals mc squared, at high enough E that maybe they're making these large mass dark matter particles. And then three, there's people like the group at IU South Bend and our collaborators who are looking for dark matter by having targets of ordinary atoms that are sitting inside of a detector, and we're looking for these targets to suddenly scatter for no apparent reason. Okay. So again, I'm going to narrow our focus down to this type of technique. I won't talk any more about these two. When we're using this technique to try to look for dark matter, one of the big complications that we have to worry about, since dark matter interacts so weakly with ordinary matter, if we have anything else going through our detector that could look like a dark matter particle, that could be a problem. So one of the big things that we have to face is that there are cosmic rays constantly smashing into our atmosphere, mostly protons boiled off from the sun, but other particles coming from distant supernovae, etc., smashing into our atmosphere, creating a rain of cosmic rays that are going through you all the time. So we have to take our detectors deep underground. In fact, our experiment and several other dark matter experiments are in what I believe is the deepest mine in North America, in northern Ontario. And so we have to go deep underground so that all of these particles get absorbed, but the dark matter particles, well, to them, the Earth isn't even there, since they interact so weakly. The other thing that we have to worry about is background from radioactivity. Everything we see around us is somewhat radioactive, because the Earth is formed from the debris of at least 2 ancient supernovae. So we have to make sure that we select all of the materials that we build these detectors out of so that they're low in radioactivity, and develop techniques to clean them. And one of the things that I worked on in a previous experiment in the same location was methods for keeping radioactivity from our air. The air we breathe is radioactive, from something that you may have heard about called radon. So we have to worry about all these types of backgrounds. That's why we have to do the experiments underground, and we have very special cleanliness requirements. So I'm going to talk about a couple of other experiments before I focus in on what we do at IU South Bend. This is an example of an experiment where essentially they're looking for the same thing we're looking for. A dark matter particle comes in, bumps an atom, and then the dark matter particle goes off on its merry way, and the atom, which is the only thing we can see here, suddenly moves for no apparent reason. This is a detector, the LZ experiment, which is based on liquid xenon. And they look for this bump, this very small energy bump of an atom, by looking at the flash of light that's created from the initial bump. And that bump also liberates some electrons, which get accelerated by an electric field up to a gas phase, and that creates a second flash of light. And what you see on the top and on the bottom are special light sensors. In fact, one of my former students is now a postdoc working on this experiment. This is another experiment that's looking for the dark matter. I guess I won't spend too much time on this, but this is another leading experiment in the field. They're looking for an atom to be bumped in a crystal that's very cold, and the way that they detect dark matter is to look for 2 signals. Again, electrons from ionization, and also very tiny vibrations in the crystal lattice that they can sense. And here you can see a photograph of modules of their detector. So now let's focus in again. Again, we're narrowing down to the experiment that IU South Bend is participating in with collaborators around the world. So we're basing our observation, again, a bump of an atom, on the superheated liquid technique. If you heat up a liquid like water, you can heat it actually above its boiling point, and unless there's a starter bubble, that water will stay above 100 degrees and sit there happily for a while if you put it in a very clean container and you don't disturb it. But if you do disturb it, it can explosively transform into a gas. And so you can amplify a very tiny signal into something that you can detect with cameras and with sound sensors. So here's an example of something you should never ever do at home. In fact, You should be careful about this. When you're heating water in your microwave oven, you can superheat water. That's water that's superheated in a glass in a microwave. And let's just play this 10-second clip. So the penny dropped in, which brought in a tiny air bubble, that's a starter bubble, and then the entire glass of water the water exploded into gas. You can get very bad burns from this, so you shouldn't try this experiment at home. Okay, so our experiment is based on that idea, though. We take a target of atoms, a fluid that we heat above its boiling point, so that it's superheated and ready to explode into a gas, and we watch it with cameras, and we listen with acoustic transducers. This is the thing that IU South Bend contributes most to the experiment on. And when a dark matter particle or some other object like a neutron or radioactive decay comes in, it starts the formation of a bubble. You can see that right here. So this gives you an idea of the overall design of the experiment, and then we put pressure on with our compression system so that we don't have that huge explosion. Our software shuts that down very quickly, and here you can see acoustic traces. We're going to get back to that. Why is that important? Why do we have these sound sensors? Well, it turns out in 2008 that the IUSB team discovered that you can actually hear the difference between different subatomic particles in matter by the sounds they make. The bubbles they make different sounds. So here is an example from a paper published just a number of days ago. This is a plot which shows number of events and how loud the event was, how loud the bubble was. And what's shown in black is the sounds that were made by neutron sources, which create signals just like dark matter will create. And what you can see is that they made relatively quiet sounds, that calibration source. When we started to look for when we looked for dark matter, all of our data appears here and here, which we know from previous work is the signature of radon decay. So the reason that the sound sensors are so important, since we can see the bubbles, is that that tells us on an event-by-event basis, hey, this isn't dark matter, this is radioactivity, which is our main concern. We don't want to confuse radioactive decay with evidence for dark matter. And these sound sensors are what lets us do that. So I'm going to play for you the world's most boring movie ever while I explain a little bit about the detector. Oops. There we go. Okay, so this is a year's worth of data in one of our larger detectors, Q60 detector, PICO 60 detector. And the cylinders you see here are the acoustic transducers. This is the region where the superheated liquid is. There's water on top to keep it away from things that could cause bubbles for reasons other than dark matter. And all we saw in the paper that we recently published was events from radioactivity. But this boring movie, it turns out, produces the most stringent limits on the properties of dark matter that could exist for a certain type of candidate. With the caveat, remember that plot with the huge range of possibilities for candidates for dark matter. Okay. So what happens if, like this time, we didn't see dark matter? That's not a failure. That just allows us to restrict what the possible characteristics of dark matter are. So we produce plots that look like this, where we plot the effective size of the dark matter, how likely it is to hit an atom, with the range of masses that the dark matter particle can have. And our lack of observation allows us to say, well, any combination of properties anywhere in this region, not possible. The dark matter does not have those properties. So let's take just one quick look at the data. This is from our recent paper. Couple of things here. The colored in regions, these are the regions that the theorists, remember these are the theorists who are trying to understand why it is that gravity is so much weaker than the other forces, and their ideas lead to predictions like this for what the possible nature of dark matter could be like. And these different colored lines are the limits produced by other experiments, including 2 previous measurements that we did, and our most recent measurement, which you can see goes down to the smallest effective size in the world. But I would caution you, this is only for one type of favored candidate for dark matter. There are other experiments which are much more sensitive than us, looking for other candidates of dark matter. Right? And to date, there's been no confirmed observations of dark matter by any of the techniques. Okay, I wanted to move on a little bit to sort of the experience of trying to do this work. So this is a montage of photographs of a typical day that I had for about 5 years. This experiment is in northern Ontario, and it gets quite cold in the winter. The radio weather guy cheerfully announced it was going to warm up to minus 40 degrees. You get onto a cage in the morning. You go down a mile underground to protect us from cosmic rays. And it's an active nickel copper mine, so it's probably the filthiest place in the world. And yet, the Snow Lab Institute has created an extraordinarily clean place, which is necessary to suppress the radioactive background, which we talked about before. Here is a recent trip that some students from IU South Bend, including, I see Tom is back there, who's, by the way, going to be demonstrating some things in the back, some interactive demonstrations that you can look at to help understand some of the work that we're doing and also some of the broader impacts of the work that we're doing in the back. And Ed Benke, who's the engineer in our group, and 2 other students, Aaron, who's now a grad student at the University of Notre Dame, and Alex Leclerc, who is a computer scientist who's now working on other things. And this is the student who's working on a competing experiment. She's now a postdoc at Penn State working on the LZ experiment, which I told you about before. What are we doing for time? I will show you 2 minutes that just give you a feeling for what it's like to live the day of a scientist doing this type of work. We won't go too long on this. Not at all. Sorry.
The Earth is constantly being bombarded with all sorts of junk coming in from space. We come underground because we have 2 kilometers of solid rock over our head. So that filters out all of that stuff that we don't want and leaves us only the stuff that we actually want to see.
So today we're in this little town in northern Ontario, and it's very early. It's still dark and it's snowing. It's not even 6 a.m. We're about to get in the car and we're gonna go to this mine where we're gonna actually travel deep underground and visit this lab that's one of the deepest labs in the world. And down there, they're looking for these little particles, these tiny bits of matter that make up the entire universe.
Scientists at Snow Lab are probing the sun and distant stars for clues about how it all came to be, and our cameras were given a rare chance to check it out. But getting there takes a while. First, we dress like miners. Then we ride with miners on their way to work in the cage, an elevator that descends to almost 7,000 feet.
So right now we're 2 kilometers underground in an active copper and nickel mine. We're hiking another 1 or 2 kilometers through the mine to get to Snow Lab, which is actually one of the cleanest lab spaces in the world. Okay, time to wash the boots.
We can't track in any dirt, so while our gear gets wiped down, we're sent to take a shower and change our clothes. Now for the science. These scientists are being lifted out of a massive cavern filled with ultra-pure water. It's shielding a detector looking for neutrinos, also known as the ghost particle.
Okay, so we're here at the Snow Plus experiment. This is what's down that hole? Like, what are these photos? This is beautiful.
So these are photos of the detector of our acrylic vessel, which is the center of the detector.
Why should we be looking for neutrinos? Why do they matter?
They're a very good messenger of the reactions that create them. We've been studying them for decades and still have more questions about them.
Discoveries made here won the Nobel Prize in Physics in 2015 by revealing that neutrinos from the sun had mass. Now, Erica and her team are expanding their search.
What are you guys looking for?
We'll be looking at neutrinos from the Earth around us, geoneutrinos, neutrinos from reactors in Canada. So that can tell us more about what's going on in the sun than the light, which takes millions of years to get out.
Wow, so we can actually study the sun from deep inside a mine.
From 2 kilometers underground.
That's so cool.
Then there's dark matter. No one has ever found it, but it's the glue holding galaxies together, and this device could detect it.
This is PICO. This is what we're using. It's the same that's actually inside there.
What is dark matter?
Right. So dark matter is, well, basically something that we don't know what it is. We don't understand about a quarter of the universe, so about 27% of the matter that's out there, we have no idea what it is.
But it's down here in this mine?
It's down here in this mine. It's all the time. It's going through us all the time. It's going through the Earth. And it'll interact only really rarely, which is, of course, it's a great thing in that, it makes it down here. We can filter everything else.
So do you think that someone, maybe hopefully you guys will find dark matter soon?
I'm really hoping so, yeah. We're getting to the point now where the limits are being driven down so far that if we don't find it soon, we're not going to find it for a while. We're going to have to think of a new way to detect it.
Okay, I think I'll stop that there. As I said, there's a human dimension to all of this. This is the IU South Bend Astroparticle Group as it currently is constituted. And there are interactive displays in the back, as I mentioned, by students to help you understand certain aspects of the work here. This is our group photo this past summer, and you can see some historical data on the 45 undergraduates who have contributed to this work, and also area high school teachers and high school students have contributed to this to this work as well. I also just want to just take this opportunity, since we're ending this discussion and getting ready for question period, just to thank all the people in the physics department at IU South Bend, especially Linda Kneffley, who helped organize tonight's event, and our guest panelists, who are theory specialists. Dr. Adam Martin is a theoretical physicist from the University of Notre Dame, and Dr. John Beacom is a physicist from the Ohio State University, and I'm contractually obligated to point out that he's a hunter for ghost particles. There are plenty of people to thank. I think there are very exciting times ahead, but I'm going to stop talking about this now. And are the people from QuarkNet here? No? Okay. All right. So I guess that isn't set up. So I guess maybe I will call our panelists up here and open up the floor to you. Questions that you have about what you've seen, anything that you want to know about.